One of the most important ideas to develop in astronomy in the 20th century was stellar evolution, the birth, life, and death cycle of stars. This has become the central idea in stellar astronomy, the great unifying model that explains the different populations and compositions of stars.
In this set of presentations, we'll be combining material from a few different chapters of the textbook to give a complete picture of the life cycle of a star. But don't worry, we've split this topic up into 4 separate lectures so you can take it in smaller pieces. In the first part, we'll look at how we can make a model of stellar evolution. Then we'll look at how stars form from the interstellar medium. We'll also have one more look at the main sequence and see that even here, stars evolve slightly. In the next part, we'll see what happens when low-mass stars like the Sun evolve off the main sequence, following all the way to their deaths and beyond to the corpses they produce, known as white dwarfs. In part 3, we'll look at the same process for stars that are more massive than the Sun and see the spectacular way they end their lives and the tiny, dense neutron stars they leave behind. Finally, in part 4, we'll see that the most massive stars in the universe have an even stranger end to their lives when they collapse to form black holes. But first, we'll have to look at the general theory of relativity, the physics that explains how black holes work.
Stellar evolution is slow. As we saw in the last chapter, the life of a star typically takes millions to billions of years, so on a human timescale, we rarely see any significant changes in a star. However, as we look at the sky, we can see stars in all stages of their evolution. There are stars forming, stars that are dying, and everything in between. Also, we understand the basic structure of stars from the study of our own Sun as well as other stars. As we saw in the chapter on the Sun, we can build detailed physical models of a star's interior using the physics of matter and energy to determine structure.
Once we have a model, we can work out how that changes or evolves. For example, hydrogen fusion changes the composition of the core from mostly hydrogen to mostly helium. When the hydrogen runs out, there's nothing to balance the force of gravity, so the core has to start contracting in on itself. This changes the outer layers of the star in a way we can observe. So we can test our models of stellar evolution by seeing if they produce the kinds of stars that we see around us. If they don't, then we know we need to refine our understanding of a star's interior to better fit the observations.
When we were looking at the Sun, we saw that there were 2 key forces that determined its interior structure: gravity and internal pressure. Remember that gravity is always matter pulling on matter, while pressure is matter bumping into matter and pushing it apart. Throughout stellar evolution, we will be returning to the balance between these 2 forces. In particular, changes in the internal pressure will drive almost all of the changes that happen to a star through its life.
Internal pressure mainly depends on how heat is generated inside the star. There are 2 important sources of heat energy for stars. Nuclear fusion releases heat because matter is converted directly into energy. Gravitational contraction releases heat because anything that falls converts gravitational energy into kinetic and thermal energy. The changes between these 2 sources of heat form a big part of the story of stellar evolution.
Finally, it's important to remember that stars start with the same composition: 3/4 hydrogen and 1/4 helium, with no more than a few percent heavier elements. Since all stars start with the same materials, the main thing that makes one different from another is its mass. So a star's mass determines its fate.
Star formation begins in the interstellar medium, the gas and dust between the stars. The interstellar medium has a low density. On average, there's only one atom of gas in every cubic centimeter of the interstellar medium. By comparison, there are 10 to the 18th atoms per cubic centimeter in the air we breathe. The interstellar medium is made of the same composition we see in stars: 3/4 hydrogen, 1/4 helium, with a couple of % heavier elements.
However, the ISM is clumpy. Some places are less dense than the average, while others are much denser. The densest clumps are called molecular clouds. Here there can be hundreds or even thousands of atoms per cubic centimeter. This is still low density by terrestrial standards, but it's high density compared to the area around it. These dense clouds are also cold, typically only 10 to 30 Kelvin. At these low temperatures, virtually all of the heavy elements, the ones we call metals, are frozen out as grains of dust.
The first step in making a star happens when the core of one of these clouds becomes dense enough that the gravity pulling all of the pieces together becomes stronger than the gas pressure pushing it apart. Remember that gravity just depends on mass and distance. So if you put enough mass together into a small enough volume, gravity can make it collapse in on itself. Once the contraction starts, it tends to speed up. As the parts of the cloud get closer together, their gravitational pull gets stronger, so the slow inward motion speeds up and turns into a free-fall collapse. As we said a few slides ago, any falling body converts gravitational energy into kinetic and thermal energy. So as the cloud core contracts, it heats up. However, at first, most of the heat this generates is radiated out into space, so the core can't get hot enough to build up a lot of pressure to fight gravity. As the collapse continues, the density of the cloud core keeps going up until light can no longer escape from it. When this happens, the temperature in the core goes up rapidly, since it can't cool off very easily. This makes the pressure build up as well, and the collapse slows down from free fall to a gentle contraction. This is what we call a protostar.
Even though the core of the star heats up from a few thousand Kelvin to over 1,000,000 Kelvin, the surface stays much cooler, since heat can't escape from the interior as easily. Remember that luminosity depends on temperature and surface area. If the star is contracting, then the surface area is going down. But the surface temperature isn't changing, so the luminosity has to go down. This continues until the heat starts to work its way through to the surface. Once the surface heats up more, the star's luminosity levels off, though it doesn't go up much because the star is still getting smaller.
Here's an HR diagram showing the steps a star goes through as it forms. The earliest stages are hard to observe directly, since they happen deep inside a cloud core. Notice the protostar phase, where the temperature is constant, but the luminosity drops. Once the surface starts to heat up, the star evolves straight over towards the main sequence. During star formation, many other things happen that affect a star's surroundings. The most immediate effect is the formation of a disk. As the gas and dust is contracting to form a protostar, some of it will have its own motion, which means that it can't fall right into the center. As the cloud contracts, this motion will be converted into a spin, which speeds up the smaller the cloud gets.
By the time a protostar has formed, a lot of the gas will be in orbit, forming a disk around the star. You can see some of these disks around these protostars. Disks like this are the first step in forming planets. So the fact that many young stars have them was the first hint that planets may be very common in the universe. Another thing we observe about protostars is that they have very strong winds and jets. The winds are really streams of gas flowing away from the star. Jets are more typically directed away from the star's poles. In this picture, you can see two jets emerging from a protostar that is buried in this cloud of gas and dust. On the left, there's an arc of glowing gas where the jet is slamming into the surrounding interstellar medium.
Our Sun has a solar wind, though it's much weaker than the ones we see around protostars. The energy for the solar wind comes from the Sun's magnetic field, and it appears the same is true for the jets and winds generated by protostars. Disks also appear to be connected to jets and winds. Possibly the disk plays a role in feeding gas into the winds. It may also help direct the jets of gas towards the poles of the star. However, the exact mechanisms are still being debated. We may need much more detailed looks at what's going on very close to a protostar to truly understand their jets and winds.
The time it takes a star to go from a collapsing cloud of gas through the protostar phase to the main sequence is much shorter than the main sequence lifetime, though it's still quite long by human timescales. As with main sequence lifetimes, the formation time depends on the mass, with higher mass stars forming much faster than low mass stars. So for a half-solar mass star, the formation time is around 150 million years, while a star the mass of the Sun forms in just 30 million years. A big 15 solar mass star forms in just 60,000 years. This is almost no time at all in astronomy. The formation process also defines the limits of how big a star can be. The maximum mass for a star seems to be between 100 and 200 solar masses. In this size range, the energy generated by the contracting cloud is so large that the light blows the outer layers of the star away, effectively limiting the size of the star. The few high-mass stars that we see like this are very unstable and tend to have explosive eruptions from their surfaces from time to time, like Eta Carina shown here. Anything bigger, and the star would simply blow itself apart before it formed.
The minimum mass of a star is about 0.07 solar masses. Smaller objects can form, but we call these brown dwarfs. Their cores never get hot enough to go through stable hydrogen fusion, so we don't count them as true stars. You can see a brown dwarf in this picture. It's that faint red dot near the middle. Brown dwarfs can have some fusion. The heavy isotope of hydrogen, known as deuterium, can go through fusion in brown dwarfs, but there isn't very much deuterium, so they don't generate heat for long. This can happen in bodies as small as 0.013 solar masses, or about 13 Jupiter masses. So that's considered the lower limit of sizes for brown dwarfs.
In the last chapter, we mentioned that we had recently added the spectral types L and T to the list OBAFGKM. Most of the L's and all of the T spectral types are brown dwarfs. When the core of a protostar reaches 15 million Kelvin, it's hot enough for stable nuclear fusion to occur. At this point, the protostar becomes a main sequence star. The main sequence is the longest part of a star's life. In the chapter on the Sun, we looked in detail at a main sequence star, and in the chapter on stellar properties, we saw how main sequence stars differ from each other in mass, temperature, and luminosity. So we're not going to spend much time looking at the main sequence here. The details of the nuclear fusion reactions also differ with mass, but the differences are not important in this class.
Stars don't change much while they're on the main sequence. However, there is some evolution that occurs over this period. Compared to what happens before and after the main sequence, these changes are quite small. But it's worth recognizing that main sequence stars do evolve. It's one of the main reasons that the main sequence is really a broad band of stars on the HR diagram rather than just a single line. The reason main sequence stars change is that their composition changes over time. Remember that the star's nuclear reactions convert hydrogen into helium. Over the course of the main sequence lifetime, the entire core of the star, around 10% of its mass, undergoes this change. The changing composition of the core causes it to contract and heat up slightly. Since the core is hotter, the star becomes more luminous. In fact, it's about twice as luminous at the end of the main sequence as when it starts.
Since our sun is about halfway through its lifetime, billions of years ago, it must have been noticeably fainter than it is today. Also, over the next few billion years, it will become noticeably brighter than it is now. This will have important effects for the Earth and its habitability in the very long term.